where what we can do is something of a thing known as like special protection scheme, or we also call it an inter-tripping scheme or cross-tripping scheme. There are so many words for this, right? So what basically we want to do is that we have a certain quantity within our parse system. So we want to measure that quantity, and once we see that this particular quantity is exceeding my required threshold, so what should happen? I should trip something, right? So this is exactly what you're looking for,
Yes.
if I'm not mistaken. Yeah. So what are the possible? By the way, we call it special protection scheme. Some other people call it cross tripping scheme, inter tripping scheme. There's just so many words for it. And if you take it on a macro level, it can convert it into a wide area management scheme or wide area protection scheme as well. Anyways, moving forward. So our question was how we can monitor a specific channel during dynamic simulation and take decision based on its value, right? So by the way, there are two ways to do it. One of the way is to do it within PSSE, and another way is to do from outside PSSE. So just to give you an idea, so the way to do within PSSE is you know that when you create your dynamic files or transient stability files, you are asked to create a connect and a connect file. So these two files are basically your linkage file, which connects your steady state model or your linear model with your dynamic model. So one way of doing is either you write a little bit of a code or adjust a bit of a code in your connect and connect files, create a DLL out of it, and achieve what you are trying to achieve. By the way, this is one of the best method. Why? Because you are trying to counter this problem internally. Another way of doing is using a hard code, or I mean countering it from outside PSSE. So how do we do this? By the use of Python. And by the way, this task is going to be tedious and it takes a lot of time. So just to get an understanding, let's do it this way. So now there are two ways to do this thing. Either you know that you have this particular quantity, and this is the quantity. This particular quantity exceeds at this particular timestamp. So if you know this, this is one of the easiest way to do. So you are performing your simulation that you know that at t is equal to say 5 seconds, this particular quantity, say voltage or frequency, exceeds my threshold. So you will go to that particular time of simulation. You will perform your remedial action scheme or your special protection scheme, and that's it.
So
Run the
here
simulation.
I have one doubt here.
Yeah,
So
yeah, yeah.
for example, if there is any variable I want to use and that is not available as measurements in the PSC, for example, PSSC measures frequency, but not rate of change of frequency. But sometimes these remedial action schemes they use rop off, right?
Yeah.
So how will I use if that variable is not even there in
Yeah, for
PSSC?
that particular purpose you will have to create your own. So this method which I'm telling you, this is like predefined, so this is not going to help you with this. So let's move to the second part of this. The If the event time is not known or your quantity is not known, right? So exactly your question, how we can counter this problem. So for this purpose, just for the sake of understanding, let me just go through this a little bit, and then I'll move with this specific problem. Okay. If you are so if this time step is not known, what you can do is you can run the simulation. So you will have to run the simulation at each time step, right? Because you do not know what
Yes.
exactly is happening. Check the event and then rerun for the next time step. So this second part, this is exactly where your answer lies. Check the event. So now you know that what is rate of change of frequency. Rate of change of frequency is your frequency. What was the frequency in the previous? Basically, you are trying to calculate this slant or tangent, right? This is rate of change of
Yeah.
frequency. Exactly. So what you will have to do is you will have to implement this rate of change or this tangent within your code. So what you're going to do is at each time step, you are going to measure the frequency, you are going to measure the time step, and then you are going to calculate df by dt yourself. And you are going to see whether this df by dt is reaching your threshold value or not. So this is how you will
Yeah,
have
clear.
to, you have to cater this problem. So when
Yeah,
I'll
I
go through the
was
code,
also
yes,
yeah, I was also thinking the same for example, time step will take at 10 milliseconds, 0.01 second, and every time will run for 0.01 second. And check that
exactly.
condition and then take decision based on that.
Yeah, exactly. Your understanding is absolutely correct. This is exactly how we are going to counter this problem. So now, just to give you an example, so I created one example code so that we can go through this, and then I'll just go through a Python program as well for you. We'll discuss each and every bit of that Python program, so that, and I'll share this. By the way, I'll share this program with you as well, so that I mean, at least we'll have a starting point. So you can start from there, tweak this code, and maybe adjust according to your own need. Does that sound good?
Yeah, yeah, yeah.
Okay, perfect. So moving along. So this is exactly now. This is the problem which I have thought, and I would like to, I mean, discuss with you. So I have a system. This is a part of a system. So here we have. Let's just assume we have a combined cycle power plant here. So it has a certain capacity available, and this is the interconnection. So what basically happens is that whenever we have an outage on this particular line, my this line starts to get overloaded because this is the shortest path for this particular interconnection. So now my this line is getting overloaded. So what is the solution for this particular problem? So the solution available with me is to, whenever this kind of thing happens, I can trip certain amount of generator, right? By tripping certain amount of units for this particular case, I can reduce the load on this transmission line. So this is exactly, I mean, this I will try to do with the help of this Python code. So moving on. So I'm not sure what kind of I mean IDE or way you are using for me. By the way, I use this Anaconda because Anaconda provides me with lots of data sciences tools. So it becomes easy to code with Python. You have all these libraries pre-installed. It becomes easy for me. So I prefer Anaconda and Spider for doing the coding. I mean, you can use whatever you want. So moving on with the code, let's see. So first of all, what I have done is in this particular code, I have created two functions. These functions have nothing to do with the problem we are going to counter. But this is from another code I was testing. So I had to tweak this code. That's why they are still there. So first of this function just checks the voltage stability. So you perform the simulation, and after the run of simulation, if you want to check whether your voltages are within your certain limit defined by your grid code or defined by your planning criteria, so you can check with the help of this. So I'll just not go through this. Similarly, there is another index which we talked during a call also, that
That
this motor spot.
SCH, that
Sorry.
SCH and SCH and ECH, they are the variables, right?
Yeah. These are the variables which are going to be passed on to. These are the arguments which are used within this
And
function.
that voltage stability check, that is the function.
That is the function. So define is a keyword within Python which is used to create a
Hmm.
function. And the thing you see in bold, voltage underscore stability underscore check underscore volt, this is the function name. And then the arguments which I am going to pass within this are two kind of arguments. In this particular case, for voltage check, I have three arguments. For the speed check, speed is basically motor stalling. So remember we discussed that in Texas or California, or where you have a huge
Yeah, yeah.
amount of motor load in your system, you can expect this following this fault-induced delayed voltage recovery, that some of the motors might stall. They may not return back to their original position due to this decrease in voltage. They may reach their maximum torque, right? So they may go into stall position. So this is exactly what I'm checking here. So this was so here what I'm doing. This is my SCH, ECH. So these are my starting channel, my ending channel, and V reference is my reference against which reference I want to check my voltage. Similarly, for the this checking the speed of different motors which I have modeled within my system. So I'm using here SCH, the starting channel and the ending channel. So what I'm doing is, if I want to check my entire simulation, the monitoring of multiple channels, within my system. So that is why I'm doing this. So instead of checking each particular channel, I'm checking a bulk of a channel at a time. And all those channels which are going to be violating my particular threshold, they are going to be reported to me. So this is how this code is written.
So
So
this
it says,
starting
yeah,
starting channel to ending channel, that means, for example, 1 to 5. So you will get 5 channels, right?
exactly. So SCH is going to be 1, my ECH is going to be 5.
So you get 5 instead of 1 and 5. You'll get 1, 2, 3, 4, 5.
1 to 5, yes.
Yeah,
So this is basically based on this. How do you plan your channels within your snapshot file? So what I
yeah,
like
yeah.
to
I
do
got it.
is, yeah, what I like to do is I like to make everything in a sequence. It becomes easy for me. So
Yeah,
let's say if I want to monitor P electrical, so initially I will select all the channels related to P electrical. Then if I want to
mm,
monitor voltage, all the voltages of all the buses in a sequence. So it becomes easy to, I mean,
yeah,
handle
yeah. Correct,
this.
correct.
Yeah. So this is my way of doing things. But anyways, you can do as like you want. So anyways, moving on. So import OS and sys. These are basically the libraries which are used for using these DOS-based commands or system-based commands within Python. So I'm using this, and this is the piece of code you must be aware of, or I
Yeah,
mean, you already
yeah,
know this code. Yes, if you want to
yeah,
link
yeah.
your PHP with your Python, you have to use this. So you are basically
Correct,
creating an
correct.
environment. Exactly. So just
Correct.
I will leave this part of the code and move on to the part which is important. So what I like to do is I create a folder. So here I have created a folder and given the path to it. So this is my path. So I mean, from the advanced automation course and whatever XYZ, you have this. So and chdr. So what it is going to do, it is going to change what wherever. I mean, why I do this particular two-step is that no matter wherever you keep your script, your Python script, your Python script is going to jump to that particular location where your models are available. So this is exactly what I'm doing. For instance, my script is available in D drive, whereas my model is available in F drive. So without, I mean, worrying about it, it is going to just move on to the that particular drive and start loading all the things from there. So this is how I do it. So save file. This is the name of my save file, and then I have the small snapshot file. Within this snapshot file, I have all the data I require. So I have all the dynamic models, I have all the channels, I have all the simulation settings adjusted in it, and it makes my life easy rather than calling the diary file and then calling the channels and then doing the setting within Python code. I try to do this. I mean, kind of these unproductive things outside Python, so that my
Okay.
piece of code becomes small. So this is how I do it. So if you see this code, just to give you an idea, this is a small model we have. I mean, it consists of
Mm,
maximum 10 or 20 buses, right? It has a 500 kV system, then some 220 kV system going all the way up to 132 kV. Some generators are there. Uh, we can, I mean, I can draw this on a single SLD, easy for me to view what is basically happening. And if I open the snapshot file for this, so these are all the channels I have. You can see all the channels. So again, as I told you, in sequence. So all the voltage first, then P
mm.
electrical, then Q electrical, and so on.
Yeah,
So this.
understood, understood.
So here, particularly, what I want to monitor is I wanted to monitor the MVA flow, right? So that is why I have this channel, and this is the quantity I'm going to measure. So for this particular case, channel number 68 is point of interest for me. Similarly, in your case, you are going to monitor the frequency. So from frequency, you are going to calculate rate of change of frequency. So again, your point of interest is going to be the frequency channel, whatever channel you want to
Yeah,
bring. Yeah. So this is how it is. Moving on. Then this is my faulted bus. So I have to create an event, and then this is my transmission line. So again, if I go here, so here I'm going to simulate a fault at bus number 500. and then I'm going to trip this line. So this is what it is. Then the circuit ID and the clearing time is zero point 0.1. So I'm going to move my simulation with this time. Again, MVA monitoring channel is 68 in my case, and the set point, the threshold which I've defined for my particular simulation is 337 MVA. So whenever my MVA capacity of this particular transmission line, which I am monitoring, exceeds 337 MVA, just do something, just strip some generators. So this is what I am doing in this case. And as we discussed, in my case, delta is 0.005. You are going to use zero point 0.1 or 0.01, whichever suits you. And these are some variables I have used. I is equal to 0, so that I can run the simulation multiple times. Then delay I am considering 1. Then this is PSSPY dot case. So here what I'm trying to do is I'm trying to call my base case, my SAV file. So my SAV file is going to get loaded, and these set of code. This is just to convert my steady state load flow case into converted case, right? So this is the first step you have to do when you perform this transient stability simulations or dynamic simulations. So this will convert my case from, this is going to
What
convert my
is the
case.
function of that order, fact, and TYSL?
So order is just creates a matrix for you. So you have to create. It's like creating a how do I put it in easy words for you? So like when you perform this load flow analysis theoretically or on paper, what basically we do is we create this admittance matrix, right? And then we solve this admittance matrix in order to get the values for different nodes within our system. This is how my mathematical load flow analysis is. So when I use this order and fact and TYSL, so I'm doing basically three things. I'm creating my state space matrix, so that I can create linear equations for each particular model within my system. So this is the reason why I do order. Then we have this fact. Fact is like creating the sparse matrix, or you'll see that some of the generators are going to be zero and or may not be operating, and some of the quantities may be zero, which are not of your concern. So within the matrix, you are surely going to see things where you have zero value available. So factorize is going to adjust this. It is going to create this matrix in a way it becomes easy for PSSE to solve this. So this is basically algorithm within the PSSE itself. And the TYSL is basically you want to make sure that your converted model is eligible or can perform switching studies. So because either I'm going to switch my load, either I'm going to switch my transmission line, or I'm going to switch my generator. So this TYSL is going to make sure that my PSSE is ready to perform this switching operations, and the results I get out of these switching operations is correct. So these are the three activities within PSSE which you can use for performing these operations. When I have this PSSE py dot restore, it is going to call my what do you call snapshot file. So my snapshot file is going to come here, and then I create an out file. You know that once you have everything ready for performing this transient simulation, you have to create one out file and give the name of an out file, right? So this is exactly what I'm doing here. So in my case, the name is this. It's a three-phase fault. I'm writing the faulted bus name and where it is going, what is the circuit ID, and what is going to be the clearing time for this particular uh, uh, fault, and then the name. So this totally depends on you, whatever name you want to give. Moving on, then PSSPY.start 0.out file. So what exactly is this command doing for you? This command is going to initialize your case. So once you when you're performing these simulations manually, you click on initialize prior to performing simulations, right? So you
Yeah,
make your simulation ready for you initialize your all your components or your channels at t is equal to 0. So this is exactly what is happening at with this command. And then psspy.run. So I am running the simulation for 1 second in steady state.
yeah,
So that
that part I understood.
yeah. So this is like pre-fault condition, right?
Yeah, till
Yeah.
line number 69, I understood.
Okay. You are clear up to 69, right?
Yeah, so 64 is PSS pi dot start 0 comma out file. What is this out file?
This out
Dot
file
out.
is yeah. If when you are
Dot
doing the
out.
simulation, the out file you give
That
where you
measurements being saved in dot out file. That one, right?
exactly, exactly.
Okay.
Yeah. So running the simulation for 1 second, then creating
Then,
a three-phase fault.
yeah,
Yep. And then because my simulation is at t is equal to 1, right? And then I have defined my clearing time as whatever I've defined. In my particular case, I have defined my clearing time as 0 point critical. It is not critical. This is normal clearing time or whatever after how much duration you want to clear the fault. So I want to clear my fault
understood.
after 100 seconds. Yep. So that is why I'm using point 0.1. So 1, my simulation is already at t is equal to 1, then clearing time is point 0.1, so I will run the simulation up to 1.1 second in this case.
Yeah,
Then I clear my fault and then I trip my particular line. Now this is where the thing which you want to do starts,
yeah,
right?
yeah. Till
Yeah.
70. Yeah.
Yeah. So here I have created one variable simulation, and this simulation just to show me that up till where I have reached. So up till now I am at t is equal to 1.1, right? So my sim variable is containing value equal to 1.1. So what I'm doing here, while my value is less than 20, so I am going to run this simulation for this simulation is going to run for at least 20 times. So you can even
20
create
times or 20 second.
no, no, it's not 20 seconds. This is
Okay,
while I
20
is less
times
than
you will run.
yes. So because so you can even create an infinite loop and break this loop once your condition is met. So this is totally up to you. How do you want to run this simulation? So here what I'm doing, sim is equal to sim plus I. So I will move to a next time step within my simulation. So now my sim will be at 2.2, right? And I'm going to run my simulation up to 2.2 second. And then I am going to monitor my channel. So I am monitoring what
1 minute.
is,
So
yes,
this sim is 1 plus CLT, and CLT is your clearing time, right?
yes.
So if it is point 0.1, so this is sim is
Sim is
1.1.
1.1, 1.1 at this instant.
Yeah, and then you are running the loop. So sim equals to sim plus I.
I. So in my case, I is equal to 1. So my starting I is, sorry, my starting I is 0. So this means I am at
Okay.
still at 1.1, right? So now from where I created the disturbance, now I'm starting to monitor my, what do you call this, channel. So how you can this particular syntax this particular API within PSSE can be used to get the value at that particular instant in Dynamics. So what I'm doing, PSSPY.channel val. This is going to give me channel value and MVA monitor channel. So this is the channel. In my case, this channel number
Okay.
was 68, right? So in your case, whatever this channel is, this is going to come here. And this one is because I'm getting the 0 is going to contain the time step and 1 is going to contain the actual value at that particular instant. So this is what I'm doing. I am getting the value of MVA, the value of the channel at sim or t is equal to 1.1. Is it clear to you?
That within green color, what is written 1? What does it mean?
One. You know that within in Python you can create list, and this list can have multiple items within it, right? So
Okay,
this
okay,
channel well has two items. This particular command gives you two items. Item number one, or any value which is going to be at index 0. It is going to be the timestamp,
okay,
and value at index number 1 is going to be the actual value of that particular channel.
Okay.
So I am interested in the value of the channel. That is why I am taking. I am more interested in value which is available at index number one.
So index number 0 would give time.
Time, yes.
Okay. Okay.
Okay. So moving on. Now I
So
am checking. So
PSS
I
pi PSS pi dot run 0 comma sim 099. What does it mean?
so this zero is print at every time step, zero time step. So in my simulation, nothing is going to be printed onto your console
Okay.
after
Yeah, yeah, I
running.
got it. And nine
So these
nine.
are, yes, and 99. So t is equal to zero. Then write every. So I am writing after every nine step. By the way, this writing is for this particular console.
Dot out
So it is,
file.
yeah. And then this is t is equal to yes. Let me know. So the first one is write every. The second one is print every, and the third one I need to check. We can check from here. So if you click on the simulation, okay, I'm not performing simulation. I just want to see. You see these three things which we get
Plot.
to do. So this is 099. So
Written
print
every.
every, write every, plot every.
Yeah, yeah. Got it. Got it.
So moving on. Now here, what I'm trying to do. So this is going to be the point where you are going to calculate your rate of change of frequency.
Yeah.
Yeah. So in my case, I did not have to perform some mathematical calculation. So I'm moving to the if part or the condition checking
Okay.
part. What you're going to do
Yeah.
at this point is, yes, you are going to calculate
I have
your
to
new
calculate
time.
the drop-off.
Exactly. So moving on, if my MVA is greater than the threshold which I have suggested, so if it is greater than this, then what I want you to do is, number one, sim is equal to sim plus delay. So what basically is this delay? This delay is like an inherent delay which we create during a time step. I mean, it is not necessary. For instance, if you want to type something instantaneously, right? You can do it at this particular time. What I am doing is, once you see that this particular transmission line is overloaded, wait for 1 second and then trip the generator. So that is why I am giving this delay of 1 second.
That you are taking care of all those relays, breakers, and this any other
Exactly.
delay.
Exactly. And then run. So now my simulation is going to run. My initial simulation time was at sim is equal to 1.1, right?
Yeah.
And then now my new time, if this threshold is exceeded, my time will go to 1.1 plus delay time. So 2.1.
Okay.
And then I'm going to run my simulation up to 2.1.
Okay.
Yep. And then again, I am trying to monitor. So what is the value now? After this passing of 1 second, whether I'm still getting some kind of overload or not. I mean, it's again just kind of playing with these things. This is a theoretical thing, but what you are trying to do will be something practical. So you have to adjust it according to your own need, right? So
Yes.
once again, I'm making sure whether still after this peak of 1 second, whether my line is still loaded or not, overloaded or not. If after 1 second my line is still overloaded, just trip one generator. So generator which is available at bus number 600 and its ID is 1, just trip this generator. And then run, once you trip this generator, run the simulation for 20 seconds. So here you see 0, 20, 099.
Is it possible to tweak any load?
Yeah, of course. You can trip load, you can trip transmission line, you can trip load, you can do anything. I mean, if you want to switch your reactor, you can switch your reactor. You want to switch your capacitor, you can do that. So I mean, with this I should put it like this: sky is the limit. So whatever you do in your steady state, you can do this. So instead of this, what will happen? You can record one. You know how to record these different commands.
Uh, Pardon?
Sorry, I think we got cut off. So I'm saying, do you know how to record different Python commands?
No, I am not very familiar with Python, so I am familiar with PSSE more or less.
Yes. So what you do? So what you do? So now your particular question, you want to trip the load, right?
Yeah, yeah.
So let's do it. How you can trip the load? So all you have to do is, instead of going all the way to the API datasheet and seeing the exact particular what do you call this API which can be used for this, there is an easy way of doing this. So just let's do it.
We can trip some
You can click on this
lines.
record.
Oh, you want to record it and then trip it and then see the code.
Yes. So test, and what I want to do is I want to switch off some load, right? So I switched off a load. So I'm just gonna press stop. Then here I am going to go, and let's see. So this is the command. So now instead of a tripping generator, I want to trip load. So I will replace
Mhm.
this particular command with this.
Oh, I did not know that during simulation we can trip load.
Yeah, yeah, you can do that. You can do that. Not an issue. I
Yeah,
think this is going. This is good up till now, right?
yeah, yeah, correct, correct.
Okay. So just let me delete this part. Okay. So moving on. Now I ran the simulation for the remaining time. So my post disturbance time is up till 20 seconds. So because what exactly I wanted to do was achieved within this particular time, right? So
Yes.
there is no need for running the while anymore. I mean, I should just come out of that. So I am breaking the loop here.
Mhm.
But if my threshold wasn't, if this if statement wasn't true, then surely I will reach this else part, right? And then
Yeah.
I'm going to continue with this simulation. So the next part is I is equal to I plus delta t, next time step,
So I equals to I plus delta t.
delta t. In my case, it is 0. So now you're simple. Let's say if this threshold wasn't reached, my I was equal to 0. So now my new I is going to be 0 plus 0.1, right? Or 0.001.
And 1 minute. So this I is
Yes.
integer, right?
This I is a floating integer. It's a float. It's a floating value. It's not an integer.
Okay.
Because I'm
I
just
mean,
comparing. So for comparing, it is not
in this
necessary that.
while loop, in this
Yes,
while
yes.
loop, you are writing that while I equals to I less than 20. So
20.0.
sim
So I
equals
am comparing two
yeah,
floating values. Yes.
yeah. So sim equals to sim plus I, and sim equals to initial value is 1.1, and then we'll run from 1.1. Okay, and then we'll check the MBA. If it is more than MBA set point, we'll run till 0 to sim. But sim is again same.
See,
Yeah.
same value is just used within the delay itself. So yes, so this is specifically for the delay. If you see,
Okay.
if I want to create a delay, then I need sim. Otherwise, I do not need even the sim value.
Yeah, so I'll suppose delay is 1, so then we'll run from 1.1 to 2.1,
Exactly.
and then we'll again measure the MVA value. If it is more than that, you will trip the line and then you will run till 20 seconds and then break.
Break, because once you go into this if, it means that your threshold has been the value you want to achieve has already been achieved, right? So after that, there is just no need of running the simulation anymore.
So this break will take you out of while loop or this if statement.
This is going to take you out of this while loop. This is
Okay.
going to take you, yes, because it takes you out of the while loop, and then you are going to come here.
Okay. And if it is not less than set point, then the first if is gone, second if is also gone, and then it is saying continue.
So continue
Continue till
means,
I equals to I
yes,
plus delta.
yes, continue means move on to the next line within your while loop.
Okay. So next iteration in the while loop, it will be you are just shifting the time from 1.1 to
One point,
1.105.
yeah, whatever your time step is, delta t is.
Mhm. Okay. Okay.
And then these this is not the part of this particular code, because I use these particular functions to monitor my voltages. So what I'm doing is, once I trip this generator, I want to see whether my system, overall system, is okay after this particular remedial action scheme or special protection scheme or not. Because I tripped one generator, so I reduce some reactive power within my system, right? So I want to make sure that once I reduce this reactive power within my system, whether my voltages within my system and these motors within my system, are they well within my range or not? So that is why just I monitored these things.
So
So,
one thing here. So is there any command to end the while loop?
uh, by breaking, so once you break, you are out of your while loop.
No, and if it is not, I mean, if it is less than set point, then
See, if it is less than set point, so it will, here you are matching, right? Here you are doing the matching. So this is where your logic comes in. How you, how you create the logic for this. So as long as my threshold value is less than my calculated value,
it
continue.
will run till 20 seconds.
Yeah, continue. So run till 20 seconds after every time step. So it is going to come to continue. Then it is going to come to this value, right? Once it comes to this value, it will see that my I has become, instead of 0.1. Hmm? So again, coming here, my 0.1 is still less than 20.0. So it comes again here. It runs the simulation for up till next time step. So now what is my new time step? Simulation is standing at, I started from 1.1. Simulation is simulation plus I. So I went to the, instead of 1.1, now I am at 1.11. And then I run for that particular time, and then again review this. So this will get
Basically,
reviewed.
you are progressing the time. So
Yes, time step. Yes,
if that line number 85 is not there, then it will be infinite loop.
yes, and not an infinite. It will end after this counter reaches 20.0.
I have one more doubt. Can I send the simulation data to
Mhm.
Excel sheet
The simulation data, yes, you can send it to Excel sheet.
from .out file to Excel sheet?
Yes, you can do that.
So I know how to send data from the PSSE raw file or .sab file to Excel sheet, but .out file I don't know how to do.
I will share with you. It is possible. Absolutely, you can send your data in the form of text file if you want. You can send your data, your out file data, into this Excel file if you want. So you have two options: either create a text file, either create a Excel file. So it's absolutely doable. So I can share this code with you. There are two ways basically to do this. The first way does not work with me because I have this latest Office. So there is some problem with my Python and interconnection of Office. So I still cannot figure out how to do this, but I will tell you the easy way. Let me just tell you an easy way.
That drag drop option I used to do, but it is, I mean, very, I don't know.
See, this is my out file. I just opened my out file within my PSSE. If you right click, you
Yes,
have an option here, export to Excel.
yes.
So if you do that, in my case, it doesn't
If
work.
I do it through
I
Python,
think, okay, it happened. Okay, that's good. So here it is. This is my Excel file
uh,
with all the data.
is it possible to do through Python?
Yeah,
Because
of
I'll
course
be
it is
running
possible.
in loop.
Yeah, it is possible. I mean, it totally depends on you how you want to do it. Now, the question is, do you want to do it at each and every time step or in the post
No, no,
simulation
yeah, post simulation at the end.
at the end? Yep, you can do it. At the end is far more easy as compared to doing it during the simulation.
Yeah, yeah, yeah.
So I can share the code with you, which you can use to do this.
Okay, okay. Thank you. So one thing is, so by next week I'll take approval for your honorarium, and then I'll contact you.
Okay, sure, no problem, and you can share
Yeah,
this as well. So hopefully,
yeah,
if you agree or if you'll give me, if you'll allow me, so I can put it on YouTube. So maybe some other students can also,
yeah, yeah.
I
Sure,
mean,
sure, sure.
you know, it is always good to help the academia. I want more people to learn this PSSE, and there are very few people all around the world, irrespective of the nationality, irrespective of from where you are. You can count these good system studies people on fingertips. So I want more people to learn system studies or power system analysis. We do need a lot of people in this field.